Hey folks, back again. Whoa, looks like you guys have been busy having a little chat before I got here. Right, okay, jazz, one of my favorite topics. All right. Edith, I always forget acids base, even though I revised it the most amount of times out of any of the topics. Yeah, lots and lots of calculations, guys. Lots and lots of calculations. Yeah, I think different exam boards approach this in different ways. It is tough, especially the buffer calcs and what have you. Yeah, I think if you can see through the numbers, I think the numbers are the scariest thing. The way they produce the questions, I think the way in which they present the questions can be very confusing sometimes, especially when they give you just as a massive block of information. And what you have to do is try and draw all that information out that's going to be relevant to you for the question. Okay. Yeah, Ruhab, I think they're tough as well for OCR. I think OCR buffer questions and acid-based questions, if you can do those for OCR, then everything else is a walk in the park, okay? Easiest and most interesting topic in chemistry. Okay, so let's have a quick straw poll then, okay? So on a scale of 1 to 10, 10 being dead, really difficult and you hate it, 1 being really easy and you think it's a walk in the park. So scale of 1 to 10 for acids and bases, please, guys, or buffers and pH and all that. So 1 being easy and it's a walk in the park, 10 being it's a nightmare and I hate it. Ibrahim says 1, Jazz says an 8 is really hard. Okay. 10 to Benyon 2. Okay, so you don't find it too bad. Oh, I mean, you guys can see with the numbers here that it depends. I mean, I tell you what, it does depend on how you've been taught it. Yeah. Hopefully the content guide videos that I've done on pH and buffers and what have you have really cleared it up for you guys. Yeah. Okay. So baked teen is one of those things that you never got to finish. Hopefully we'll go some way to doing that for you. NMR's the worst. Yeah. NMR does suck. Yeah. You're right there. It absolutely does suck. So what are we going to do? Well, actually, in acids and bases, there's not a lot to it. There really isn't. In terms of content, the size of the content, then there's not a lot to it. Do I take it, ladies and gentlemen, that we want to do something on NMR, especially on NMR when we do organic chemistry in a few weeks' time, in a couple of weeks' time? Is that right? Do we want to do NMR? I got you guys covered. Don't you worry about it. Make sure that it's clean, concise, to the point, right? Yeah. It does tie in the whole of organic chemistry. You're right. Yeah, absolutely. Those NMR questions bring in other things as well. Anyway. Acids and bases. Let's do that. So what do we need to know? In a nutshell, it's this. So we have got, working from the top right-hand corner, first of all, we've got our definitions. You need to know your definitions of strong acid, strong base, weak acid, weak base, so on and so forth. You, of course, then need to calculate pH, and you need to do that for 3 things, all right? Strong acids and weak acids, and then strong bases. We do not do weak bases at A level. Okay, that's something called KB, which is not in any of your specs. Okay, so not in AQA, OCRA, or EdXL. It may be in like an international baccalaureate or an international exam board or something. I don't know. We don't do them. But yeah, essentially, anybody that's doing domestic UK ones do not need to know KB. And linked into strong bases is that little thing called KW, which is the ionic product of water, which you do need to know about. And it's the only, well, it's not the only way. It is the way in which the exam boards would like you to calculate the pH of strong bases. Moving on from that, we've got pKa and pKw. All right, so these are, well, it's like pH, okay? So if you can calculate pH, you can calculate pKa and pKw. That then ties into pH curves, which is the main practical element associated with acids and bases. And then we've got buffers, which, you know, everyone finds really easy, don't they? So what we're going to try and do is we're going to try and start with some definitions and some brief calculations, pK, pKw, bit on pH curves, and then hopefully we'll have a decent amount of time left at the end to talk about buffers, because I know that is the one thing that you guys really, really struggle with, okay? Is there such a thing as pH 20? I would say, ooh, no, probably not. Although I know pHs can actually be negative, but I don't think you can go to pH 20. Okay, super acids and super bases, maybe. Yeah, I suppose if it is possible to go past pH 14, if it is possible to go below 0, then it must be technically possible to go past pH 14 as well. Yeah. So definitions. I'll tell you what, I'm not even going to write this down. We don't need to write this down because it should be something that's ingrained in your brains already. So definition of a strong acid is that they all do what? Answers in the chat, please. Okay, so strong acids. Examples will be HCl, HNO3, H2SO4. Yeah, good. Fully dissociate. Good. Fully dissociate in solution. So you get a solid, like regular one-way reaction arrow, and they fully dissociate in solution, releasing all of those hydrogen ions. Okay. Now for a weak acid, definition here, ladies and gentlemen, as I give you a couple of examples. So that is ethanoic acid. Another weak acid would be, I don't know, HSO4 minus. Okay, that's technically a weak acid. Yeah, only partially dissociate. So they exist in equilibrium. Okay, they exist in equilibrium. But 99 times out of 100, any weak acids you come across are going to be your organic acids. Okay. So this time, strong base, again, they fully dissociate, releasing OH minus ions into solution, fully dissociate, and a weak base exists in equilibrium, okay? So strong bases are our alkalis, okay? So sodium hydroxide, I don't know, barium hydroxide, things like that. A weak base, for example, would be NH3, okay? So rather than releasing hydrogen ions, what do? Instead of releasing hydrogen ions, because NH3 cannot release a hydroxide ion. So strong bases release hydrogen ions fully. Weak bases, hydroxide ions. Strong bases release hydroxide ions fully. Weak bases accept protons, Matilda, absolutely. Okay, so these accept protons. Now, why does that make them a base? Well, usually water dissociates into H plus and OH minus. Okay, if all the NH3 is sucking up those H pluses, what's going to happen to this equilibrium? It's going to shift and it's going to produce more of those. So it's a knock-on effect with a weak base. Okay, weak bases are proton acceptors. They shift that equilibrium, that natural equilibrium of water, to the right. Therefore, more hydroxide ions are produced, and that's, of course, how they make them make it basic. Okay, so we must always remember our essential definition of acids and bases. Acids are proton donors. Bases are proton acceptors. Okay, acids are proton donors. Bases are proton acceptors. That's the Bronsted-Lowry definition of an acid and a base. There are Lewis ones as well, T-Boys mentioned in there, but we don't have to go down that road, okay? You do not have to go down that road at A-level. You don't have to talk about Lewis acids and bases at all, okay, as far as I'm concerned. You can always just rely on your Bronsted-Lowry theory, okay? So calculating pH, all right? So calculating pH. So first up, strong acids. So generally speaking, pH equals what? Oh, yeah, Matilda, a little bit. Yes. All right, a little bit. Boom, Benyon, straight in there. Minus log to the base 10 of your hydrogen ion concentration. Okay, of course, we can flip that. If we want the hydrogen ion concentration, that equals 10 to the minus pH. Boom. Okay, so those should be ingrained in your brains. All right, so minus log H plus concentration, and of course 10 to the minus pH is the inverse. Okay, pH should be in 2 decimal places. Yeah, you're absolutely right. That's the common accuracy in which we calculate pH to. And amphoteric does mean it can act as an acid and a base. Yeah, absolutely. It can. Thing is, we do need to get into that whole Lewis explanation of an acid and a base there. Okay, so we're not going to get into that. But strong acid. Okay, how do we find the pH of a strong acid? Well, first thing I'm going to say, whenever a question asks you, find the pH. Okay, so let's say you see a question that say, calculate the pH of blah, 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 and they give you all that information in the question. They calculate the pH. First thing I do when I see a question like that, I cross out pH and write hydrogen ion concentration. The reason is the only way in which you are going to find the pH of something is by finding the hydrogen ion concentration. And it just makes it a little bit clearer. It makes it easier to find the hydrogen ion concentration, because that what they're asking for is like once removed the pH. If you just say to yourself, right, well, I need to find the hydrogen ion concentration, it just sets your mind into a mode of thinking that's really helpful whilst doing the question. Okay. Jazz, you are absolutely right. And that's the first thing I'm going to say here. So as all strong acids dissociate fully, hydrogen ion concentration, okay, is proportional to the acid concentration. Okay, now I say proportional because it's not the same. Okay, so if I know that I have got a 0.2 mole per decimeter cubed solution of HCl, what's the hydrogen ion concentration? If I've got a 0.2 molar concentration of HCl, what's the hydrogen ion concentration? Good. It's also 0.2 because we know HCl dissociates to H plus and Cl minus. This is 1 to 1. Okay. However, if I've got a 0.2 mole per decimeter cubed solution of H2SO4, the hydrogen ion concentration here would be 0.4. Absolutely, because this is H2SO4 that dissociates to 2H plus and SO4 2 minus. So this now is a 1 to 2. So just be careful with your monoprotic and diprotic acids. Okay, just be careful with those. You need to spot them. All right. So quick question then. Okay. On strong acids, I want you to calculate the new pH when 100 centimeter cubed of water is added to 50 centimeter cubed of 0.05 mole per decimeter cubed HNO3. Okay, so calculate the new pH. I'm going to give you guys 2 minutes to do that. 2 minutes to do that. And I just want you to put your answer when you've got it in the chat. Okay, and I literally just made that up, so I'm going to work it out as well. Okay. Don't worry, we'll talk you through it. Wati, apologies for the pronunciation there, if I got it wrong. 1.78, 1.6 from Matilda. We have got 2. So that's 3 answers and 3 different answers there. I know one of you's right. .3 recurring. Interesting. 1.6 from T-Boy. Okay. So first thing I'm going to do is find the concentration of hydrogen ions initially equals 0.05 moles per decimeter cubed. Okay, because it's like we said before, this is a monoprotic acid. Okay, so it's the hydrogen ion concentration is the same as the acid concentration. Okay, now what happens to that? We dilute by adding 100 centimeter cubes. So what's going to happen to this concentration? It will decrease. Absolutely will decrease. And in fact, I'm going to divide it by 3. The reason I'm going to divide it by 3 is because 50 is a third of the new total, which is 150 centimeter cubed. So it's going to be diluted by 3 times. Okay, it's going to go down by 3 times. So I've divided that by 3. Okay, so what's that? So that is 0.05 divided by 3, and that equals 0.016 recurring moles per decimeter cube. That is our new hydrogen ion concentration. So to find the new pH equals the minus log of that answer, which is 1.78. And that is our new pH. Okay. So these dilution questions, they do like to ask you, but it's you can work it both ways as well. They may say, okay, this is the pH of 100 centimeter cubed of HCl. What's the concentration? So you can reverse engineer this as well. So I divided by 3 here because the volume's increased by a factor of 3. So it's gone from 50 to 150 centimeter cubed because we've added 100 to it. Yeah. So that's increased by a factor of 3. So that means it's diluted by a factor of 3. Is that all right, Fatima? Oh, if you did it the moles way, you should get exactly the same answer. Yeah, if you did it the moles way, you should get it in exactly the same answer. So you find the number of moles and just, do it that way. I've kind of taken a bit of a shortcut here, but okay. So strong acids are actually fairly straightforward. You just need to remember this. Okay, you just need to remember that so you can, and you know what, that's going to be the final step in any pH calculation you do, whether it's for strong acids or weak acids or what. Okay, now the moles way is basically using concentration and volume. So you can use concentration times volume gives you the number of moles, and once you got the number of moles, you can divide that by the new volume, which will give you the new concentration. So it's kind of like you do the same thing, but you're just doing it like the long way workaround. Okay, that's all it is, Rasep. So what do we do next? Well, I'll tell you what. Let's do weak acids since we're on it. Okay, now, of course, what we need here is our acid dissociation constant. Okay, now, if you know how to do Kc, you know how to do this. Okay, so let's say we've got a weak acid and it partially dissociates into this. Okay, now, good. All we need to do to find Ka is the same as Kc. It is the concentration of, those of you that need to know, OCR, let's say, that is our conjugate base, over the concentration of the acid in full. Okay, that's it. Perfect. Thank you, Isabel. Yeah, so it's H plus A minus over HA. So it's the dissociated acid, so the H plus and the conjugate base over the concentration of the acid. Okay, so what do we need? What sorts of questions? I'm not going to go through on with you because we'll be here ages doing these, but what sorts of questions can they ask you? Sometimes they can ask you to find Ka, and they might give you the concentration of the acid, and they'll give you the pH. Okay, so if you've got, let's do this in a different color, the concentration of the acid, which is this one, and you've got the pH, how do we go about it? What's the first thing you do in this question? If you want to find the Ka of this acid, you've got the concentration of the acid and you've got the pH. What's the first step? Boom. Absolutely. Okay. So step one, find the hydrogen ion concentration using 10 to the minus pH. Boom. Okay. In terms of words, what's the calculation like? What are we timesing and dividing? Like literally concentration. So it's a concentration of the negative ion times the hydrogen ion concentration dividing by the concentration of the acid. Okay. So you find the H plus using pH. What's the next assumption what's the assumption we're going to make then? So we've got this and we can find this. Okay. What about this? How do we find the CH3COO minus concentration? It's using an assumption. Excellent, Matilda. Yeah. So we can assume that the concentration of H plus equals the concentration of the A minus being that in this case. Okay. So what we do know, therefore, we can say that Ka equals H plus squared over CH3 COOH. Okay. That's when we do H to the power 2. That's it, the square. Okay. We don't need to square root it. It's not a square root, it's the square. Okay. That's it. We use it there. Okay. So we're making that assumption. We cannot make a hydrogen ion without making an anion. Okay. So when you make one, you have to make the other. All right. It's like having a pair of shoes. All right. So you can't split the shoes up without on the left one and the right one. Okay. So that's it. So why do we square it? Because these two values are the same. So if H plus equals 2.0 and A minus equals 2.0, you can write 2.0 times 2.0, or you can just write 2.0 squared. Okay, that's why we're squaring it there. Oh yeah, that's Bruhab. No, do not even mention the B word until we get there. Okay, let's not confuse matters. So Ka equals H plus squared divided by that. So you are done. Okay. Edith, if you are given the concentration of CH3COO minus, then you don't even have to calculate the H plus. Again, you can just assume it the other way in the opposite direction. So if you know you've got the CH3COO minus concentration, you know the H plus concentration is going to be the same. Okay. So I'm guessing they don't give you the mark if they ask for the formula. Oh, right. Good. Yeah. So if they ask for the expression for Ka, I would definitely write the full expression. Definitely write the full expression. But for the purposes of calculation, you can write H plus squared. Okay. So that's how we do that. Another thing, let's do a different color. Let's say they want you to find the pH. Okay, so how do we find pH? Well, we have got Ka. I'm just going to use this expression just to make it quicker. We need to rearrange it. Now, remember, what did I say? If they're asking you to find the pH, what are we really trying to find? That's all right, Matilda. No, you ask away. That's why I'm here. If they're asking for pH, what are they asking you really for? Yeah, the H plus conc. Yeah, that's it. This the H plus conc they want. So what I would do here is make the same assumption as we just did. So I would write Ka equals H plus squared divided by HA. Because again, you don't know that. You don't know the A minus. So I'm just going to write H plus squared over HA. So therefore, the concentration of H plus squared equals Ka times the concentration of HA. Okay. And then once you've got your answer, all right, you need to square root it, and that gives you the hydrogen ion concentration, and then that gives you the pH. Okay, good. Some of you are a little bit ahead of me on that, which is awesome. All right. So if they're asking you to find the pH, those are the steps that you take as well. So if you're given the Ka and the conc of the acid, that absolutely it, Edith. Absolutely it. That's exactly what I'm talking about. Okay. So these aren't too bad. All right. It's just that the assumption that we've just made, and Ruhab touched on it, and he's, you know, I did kind of slap his wrist for mentioning it, but you can't make the assumption that these two things here are the same. In a buffer, you cannot make that assumption. Okay. You cannot make that assumption. Okay. I'm going to try, Fatima. I'm going to try. Okay. So what are we going to do next? Right. KW, really quickly. This is whistle stop tour. Don't forget. So in terms of weak base, no, not weak base. We don't have to do that. Strong base. Okay. If we want to find the pH of a strong base. Now, you don't have to be sorry, mate. What we need to know is this. The water, right, because the pH, there's no two ways about it. pH is the minus log of the hydrogen ion concentration. So if you've got something like potassium hydroxide, okay, that splits into K plus and OH minus, then there's no H plus in there. There's literally no H plus in there for you to use to calculate the pH. That's why we need KW. Now, water naturally splits into OH minus and H plus, like so. There's this natural equilibrium in water. Okay. How do we know that? Well, pH 7 is neutral. That is a particular amount of hydrogen ions that water has got in it. Okay. Yes, it is. So we can find the dissociation constant for water. KW equals H plus times OH minus over the concentration of water. Now, what's the concentration of water, really? I mean, can you find the concentration of pure water? No. All right. It's kind of like infinite, right? Yeah, it's a lot. It's basically, yeah, or you could call it one. Yeah. You can absolutely call it one. Either way, that is your KW. Okay. So KW, that's it. That's it. Well, we do assume that, Jazz. We do assume that, although it does change with temperature. And actually, that is something a lot of the exam boards are picking up on in questions recently, is, you know, the change in that in temperature. So for me, okay, this is an exothermic reaction, bond breaking, as I was saying in just the year one a minute ago. And this is an endothermic process. So if you heat water up, okay, if you heat water up, which way is it going to favor, the right or the left? Which way? A bit of Le Chatelier's here. If you heat water up, it's going to favor the left. Good. It's going to favor the left. If you increase the temperature, it's going to favor the endothermic reaction, bringing heat energy in, okay, to form water. All right. So what happens to the hydrogen ion concentration? It goes down. Well, both of these go down. Okay, so the value for KW is going to change. The value for KW is going to change, but the pH pH changes slightly. Okay, but it's still classed as neutral. It's still classed as neutral. I know we haven't got time to get into it, but whatever temperature water is at, it's still classed as neutral. The reason being that whatever happens in pure water, the hydrogen ion concentration always equals the hydroxide ion concentration, assuming it's pure water, because you can't make one without the other. So whilst the pH will change, okay, because you've got fewer hydrogen ions in there, because it's shifted to the left if you've heated it up, it's still classed as neutral because what's neutral is when hydrogen ions and hydroxide ions are balanced, they're equal. Okay. So how would they phrase a question on that? I've seen a couple whereby it's like, right, calculate the, what will happen to the pH of water if it's heated up? Is it still classed as neutral? That's the most common question I've seen. Okay. One student says it would still be neutral. One student says that it wouldn't, explain which student's right. All right. So it's just a tricky little one, that. So point is here, ladies and gentlemen, that if you wanted the pH of a strong base, there are a few steps. Number one, you find the OH minus concentration. And it's the same as that as what we did for strong acids. If you know this is a 1.0 mole per decimeter cubed KOH, you can assume you've got 1.0 moles per decimeter cubed of OH minus. Okay, so it's just the same. Be wary of your dibasic ones. So calcium hydroxide, for example, and stuff like that. Okay. Why is it exothermic that way? Well, you're bond breaking, aren't you? Whoa. Thank you. Rewinds. This is endothermic. We're actually breaking bonds, putting energy into break bonds. This is exothermic. Thank you very much. So we shift to the right, blah, 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 blah. Sorry, guys. It's what happens when I talk and write at the same time. That's what happens. Okay. Spot on, guys. Thank you for keeping me on the straight and narrow there. Okay, I do know what I'm talking about, I promise. Okay, so find the OH minus concentration. Secondly, okay, plug that into your KW expression, which is H plus OH minus. But of course, if we're going to stand any chance of finding pH, we need to rearrange it, and that means H plus concentration equals KW divided by OH minus concentration. Okay, Ibrahim, you gotta watch me, mate. You gotta watch me. So if anything comes up like that, do not be afraid to question me, my friends. Okay, it's teamwork here. So that is how you find your hydrogen ion concentration, and then that is how you find pH. Okay. So that was my next point, Raseb. If you are not given the data, okay, it is 1 times 10 to the 14. Okay, KW in standard conditions is 1 times 10 to the 14. Okay, times 10 to the minus 14, in fact. Okay, so 1 times 10 to the minus 14. So it's quite, I would say, a straightforward thing to do is to find the pH of a strong base. Okay. Yes, you do assume if not given the data, it's 1 times 10 to the minus 14, okay, as your KW. All right. So that's it. That's how you do that. Okay. So find the OH minus concentration, rearrange your KW, and that's it. It depends. In EdXL, I think it is in the data book. In the other exam boards, they'll remind you in the question. Okay. But it's easy number to remember anyway, 1 times 10 to the minus 14, because it's 1 and pH goes up to 14. So there we go. So that's strong bases. Now buffers, how do they work? How quickly can we do this? Okay, so acid buffers. We need 2 things. We need 1, a weak acid, and we need 2, the salt of a weak acid. Okay, so e.g., let's keep it simple, ethanoic acid and sodium ethanoate. Okay, or I suppose you could write it like, okay, Jazz, they do indeed. They resist small changes in pH when acids and alkalis are added to it. Okay, this is what we do. So what we have to remember, at the heart of this are just weak acids. We have just covered how to find the pH of a weak acid. Okay, at the heart of it is our Ka expression. So if we're using this as a buffer, so our ethanoic acid, Okay, so Ka equals the concentration of ethanoate ions times hydrogen ions all over our acid. That is at the heart of what's going on in terms of calculations for our buffers. Okay, so hopefully I can help you out with this. So in any buffer, okay, in any acid buffer, we have got an equilibrium set up. So Le Chatelier's is also at the heart of this. So this is CH3, C minus, and H plus. Okay. So normally in a weak acid scenario, when you've got a solution of a weak acid, where is most of the acid? Is most of it on the left or most of it on the right? Do most of it stay as this, or does most of it get dissociated? Where is most of it? That's what I'm asking. Left or the right? Boom, on the left. Okay. So over here, I want you to think of it like this. We have a stockpile of CH3 COOH. Okay. Now, in a normal weak acid situation, you'd have loads and loads and loads of this and very little of these two things. This equilibrium lies naturally to the left-hand side. Okay. So very few hydrogen ions are released, which makes sense because a weak acid has quite a high pH. It's like pH 6 or something like that, right? So we haven't got many hydrogen ions. Most of it exists over here. Vast majority of it, it's got a really small Ka value, like 10 to the minus something, okay? So what happens here? Yeah, it partially dissociates. Only a tiny amount dissociates, okay? So let's think about this stockpile, all right? What if I added some potassium hydroxide to this? What's going to happen? What's the potassium hydroxide going to react with? Of those three things, what's the potassium hydroxide going to react with? Taran says the H plus. Ibrahim says the H plus. CH3 COOH. Okay, it reacts with the H plus. Well done, guys. It reacts with the H plus. So what happens to hydrogen ion concentration? Therefore, hydrogen ion concentration goes down. Okay, so this is actually this is neutralization, of course, isn't it? The OH minus from the potassium hydroxide reacts with the hydrogen ions to form water. Okay, so as a consequence, all right, what needs to happen? If your hydrogen ion concentration decreases, in terms of Le Chatelier's, then what happens to the equilibrium? Good. The equilibrium shifts to the right. Okay, it shifts to the right. Good. Increase in dissociation. So more of this gets turned into CH3 to C minus, and therefore, whoops, maintaining the hydrogen ion concentration. So the potassium hydroxide's gone in and gobbled up all the hydrogen ions, and the equilibrium's like, no, I'm going to make more hydrogen ions to replace them and maintain the pH. So that equilibrium just shifts to the right, okay? Now, why is it able to do that? It's able to do that because we've got a massive stockpile of these acid molecules, all right? So yeah, got plenty where those came from. Yeah, keep them coming. Give us loads of hydrogen ions. We'll replace them and maintain the pH, okay? So yeah, both of these will increase, okay? But what we're really concerned about is the change in pH. And of course, what affects the change in pH is the H plus, okay? So let me just get rid of all my scroll that I've just done from there, which I can't do. Oh, damn it. Sorry, guys. I have to restart it. There we go. Right, back in the game. Okay, so that's how acid buffers work when you add an alkali to it. Okay, so we need that stockpile of acid on the left-hand side to dissociate more, just in case you add some alkali to it, and get your H pluses back to a level at which they were before. Okay. Oh, yeah, absolutely, Edith. When we apply it to questions, it does make more sense. Okay. Now let me change my color to blue. So what if I added some HCl to it right now? If this was just a weak acid and we added some HCl to it, it wouldn't buffer. Why would it not buffer? Ah, Courtney, we're getting to that. We're getting to that. If this was just an acid and I added some HCl, we increase the hydrogen ion concentration and the equilibrium, that was rubbish. And the equilibrium shifts to the left. Okay, sorry, there's a bit of a delay. I was waiting for the delay to come in. Yeah, absolutely. And it shifts to the left. So equilibrium shifts to the left. Okay, because we're increasing this. The equilibrium is like, no, we need to bring that back down, maintain the pH and go that way. Now, the only way in which they can do that is by combining H plus with CH3 C minus. Now, as we mentioned previously, in a normal weak acid, we have got a very small amount of these. So it is completely unable to act as a buffer. Okay, if you've only got 2 molecules of these and you flood this with 200,000 hydrogen ions, well, only 2 of them are going to be able to make it over to the left-hand side, okay, because you've run out. This is where your salt comes in, whoever it was that was asking. So this is a stockpile of CH3 C from the salt. Okay, so the salt provides the extra A minus, Matilda. Absolutely couldn't have put it better myself. So that is why we need that salt there, because without the salt, we cannot shift the equilibrium to the left, because the hydrogen ions that we've added to it by adding HCl or something like that have got nothing to react with to actually form and shift the equilibrium to the left. Okay. Don't you worry, Edith. I got you covered. I got you covered. All right. Literally do a month with TT and it will straighten things right out for you. I promise you that. Okay. So does that make sense, guys? So we add HCl, we increase hydrogen ion concentration. Therefore, the equilibrium shifts to the left. The CH3, C and H plus combine to form the CH3, C minus, and that's it. Okay. Oh yeah, PMA, guys. Yeah, buffers do suck. Buffer questions do suck. Okay. So that's how an acid buffer works. All right. So that's why you need your stockpile of acid and your stockpile of salt. One allows it to move one way, one allows it to move the other. Now, just a quick one. In terms of calculation, so buffer calculation, okay, they can come in lots of different forms, all right? But I'm just going to tell you this. It does all rely on your weak acid dissociation constant, okay? It all relies on that. Now, if they're asking you, there are base buffers. Yeah, there are base buffers. I believe not everyone, but I think AQA need to know how they work, but you won't be asked questions on it. Calculation. Okay. So in terms of calculating buffers, okay, so what you'll be given, okay, a standard buffer question, you'll be given this, okay, let's say the pH of the buffer. Let's say you're asked to find the pH of the buffer. Don't forget, you're being asked to find the hydrogen ion concentration, aren't you? So you've been given the Ka, you've been given the HA, okay? So let's say you've been given the initial concentration of the acid, you know the Ka for that acid, okay? Now, what we cannot say here is that these two are not equal. So we're not dealing with a weak acid here. We're dealing with a buffer. This comes, yes, from the weak acid, but this here, what is that A minus in respect to the in respect to a buffer? Okay, what is providing that value there for the A minus? Boom, the salt, absolutely. Okay, so this is basically the concentration of the salt, and this here is what you need to find. Okay, so if you wanted the pH, you could rearrange this to say that H plus equals Ka times the concentration of the acid all over the concentration of the salt, and then that will give you your pH. The tricky things that happen, okay, are the ways in which you get this data. If you were just given these 3 bits of information, finding the pH is easy, right? If I gave you those 3 numbers, could we all put that into our calculators to find the hydrogen ion concentration? Yes or no? If I gave you those 3 numbers, yeah, of course you could. You can do one number times another divided by another. It's not rocket science. The difficult thing is, okay, and this is where the practice comes in, it's being able to find those bits of information, to get the right numbers to put into this equation at the end. So the calculation itself, I want you to remember, is a walk in the park. It's timesing 2 numbers together, dividing by another one. That's all it is. But the difficult bit, your journey, the bumps in the road, are going to be finding those bits of information, finding those numbers to start with. And hopefully that's what we're going to put to bed tomorrow. I'm going to put 3 different calculation questions. I tell you what, in terms of doing some questions tomorrow, we haven't even covered pH curves, guys. We haven't even covered pH curves. I'm going to show you something before we finish. Okay. Would we just like to do some typical buffer questions tomorrow, and I'll show you how to get through them? Would that be helpful? I'm waiting for the answers. Why isn't A minus equal to salt plus dissociated acid? Yeah, there are assumptions that we need to make, and we'll talk about them tomorrow. Okay, the assumption is when we do these that none of the acid dissociated. I know it sounds ridiculous, but trust me. Okay, so yeah, we'll do that tomorrow. Then we'll do that tomorrow. Yeah, we can start with a simple Ka question. Yeah, absolutely, and we'll spend most of our time tomorrow doing some buffer questions. Sounds like a plan. Okay. Now, the last thing I want to show you is this. I'm not going to say anything. I'm just going to show you this. In fact, I'm going to stop sharing just for a second. And I'm going to bring this up. This one. Okay, so what you should be seeing now is a snapshot from the content guide. Okay, so what pH curves can tell you. Now, without going into pH curves in too much detail, this here basically tells you everything, every bit of information you can get from a pH curve. Okay, so when you've got your pH curve, typical things that you can find out are this. Okay, let me use a green because there's no green on here. One is the initial pH of the acid. Okay. Yeah, that's it, Matilda. Do you need to know how to prepare buffers? Yeah, well, those are the types of questions they can ask you, aren't they? Okay, those are the types of questions like, oh, if you added, this much salt to some acid, or if you added this much alkali to an acid, you'd make a buffer. Why? And what would be the pH of the buffer? So they're tricky. They really are tricky, and we'll make sure we include one of those. But just to finish off with today, things that pH curves can tell you. One, the initial pH of the acid, okay, or the initial hydrogen ion concentration. You can find that. So let's say we've got an acid and we're adding a base to it, okay? We're adding an alkali to it, so pH is increasing, okay? So you're starting, that's the initial pH of the buffer. here is your equivalence point. Okay, so that's where it neutralizes. So up here, where the levels off, this is the pH of the base. Okay, so you can find the initial pH of the acid and the pH of the base at the end. You can use Kw to calculate the OH minus concentration, or indeed the concentration of the base. So that's something else you can find from this pH curve. Suitable indicators, that's another thing they can ask you. Oh, which indicator would be best for this pH curve? Literally, you just pick one from a list. That's all it is. Okay, that's all it is. Now, great one, this one. Calculate the Ka for the weak acid. Okay, calculate the Ka for the weak acid. Now, all we need to do is find the volume of base needed to reach the equivalence point. So this point here. So this is A. Okay, so you find the volume of the base. You halve it. So that takes you to B. Now at that point, we read the graph, and at C, pH at half volume equals the pKa. Okay, so when you've got a pH curve and they want to ask you a difficult question, the most difficult question they can ask you is, what's the Ka of the acid? If it's a weak acid, then all you need to do is find the volume at which neutralization happened, halve it, and then read the pH at that point, and that equals pKa. Okay. Now, why is that? Well, let's look at our Ka expression. Ka equals H plus X minus over Hx, or H plus A minus over Ha, whatever. Okay, that's fine. But the thing is, at half volume, okay, the number of moles, or the concentration of acid, equals the concentration of salt. So half of the acid has been neutralized. So let's say you started with 10 moles of acid, then you end up with, at half equivalence point, okay, you end up with 5 moles of acid still unreacted and 5 moles of salt that's actually been produced by the reaction. Yeah, so you started with 10, halfway through, you got half of it has actually reacted and become a salt. So this, half of it is unreacted, still the acid, which is this. So that's why they cancel each other out. So therefore, Ka equals the hydrogen ion concentration. Absolutely. Okay. And if Ka equals hydrogen ion concentration, well, what if we just did minus log to the base 10 of each of those things? Well, we end up with pKa and pH, don't we? And that's why pKa equals pH at that point. Okay. So why is A minus equal to HA? Because, like I said, if you've got, let me just stop sharing for a sec. If you've got 10 moles of acid, okay, and at neutralization point, okay, when all of that acid has been neutralized, all 10 moles have been reacted. Yeah. But at half equivalence point, at half neutralization, 5 of them have been reacted and turned into a salt, your A minus. Okay. 5 of them remain unreacted and still acid. So at half equivalence, or half neutralization, you've got 5 HX and you've got 5 X minus. So in other words, they cancel out. You with me, Benyon? Fingers crossed. That's it, Ibrahim. Dim problem. Right, I'm going to go because I've got a meeting in 5 minutes. So thank you very much for coming along, guys. Hopefully I've shed some light on some pH stuff for you guys. Okay. Yeah, you know what, guys? One last thing I will say today is that we are hoping for some more news this week. We're hoping for some more news this week on grades and stuff like that. So keep an eye on the media. All right. I'm sure they've got to give us some more clarity about this whole uni situation and calculated grades and exams and stuff. I'm hoping that's going to be before Easter. You would like to think that they'd make a big announcement before Easter. That's all. Literally, I'm just guessing. I'm keeping my fingers crossed we're going to hear before Easter. Easter holidays were meant to start on Friday for most people. So, yeah, I'm hoping, fingers crossed, we're going to hear some more by then. And as soon as we do, you can rely on us to just get straight on YouTube and just try and make sense of it all for you, okay? And just answer your queries and questions and stuff like that, okay? So make sure, if you're not subscribed, guys, make sure you are already subscribed to our YouTube channel. Make sure you hit the bell to get reminders when we're live, because you know if there's an announcement one morning, we're going to be, boom, straight on YouTube, and you want to know and you want to get involved, okay? So make sure you subscribe and hit the bell, and yeah, we'll help you guys out as much as we can. So thank you very much, guys. I will see you tomorrow for some pH questions and some buffer questions and stuff like that. Okay, so take it easy. Thank you very much. Spread the word. Okay, make sure you give us plenty of likes in these videos as well. Share the love. And yeah, I will catch you guys tomorrow. Bye-bye.